Okay, so I want to do a quick little application with you around torque. And so this is just comparing biceps to brachioradialis. And I'm going to do it really quickly with you. This is an exercise that you should be able to do now after viewing what torque is with the angular force. So I'm going to draw two little systems here. Again, I'm using the humerus and the radius and the ulna. I'm going to draw on the axis here. And I'm going to draw it here. Again, humerus, radius, and ulna. And I'll just put your hand on here so that you know what system we're talking about. So you should know, because we just finished working on the elbow, that the biceps comes down, inserts on the radial tuberosity. So that's its point of insertion, or where it exerts its force on this lever system. And brachioradialis comes down and inserts on the radial styloid process. So way down here near the hand. So their insertion sites on this lever are different. And so that's where we can have a little bit of difference in application, and that's why it's really fun. And this will be a test of whether you really truly understand the concept of torque. So remember, torque is angular force, and so we're wanting to determine what the torque is happening at this system, both elbow systems. So I'm going to label a few things, and then I'd like you to pause the video, and I'd like you to try and see if you can figure out what's going on. So I'm going to label. And so there we have that one labeled, and then I'd like to label this one as well. Okay, always label your axis. That's really nice to give you sort of a centering component. Okay, so here's our application, and what we're going to do is we're going to bring in torque and we're going to apply it to levers. And then I'm going to do one final thing, and I'm going to apply it to muscle contraction. Okay, so we're going to get what kind of lever it is first, and then I'd like to talk to you about the different types of muscle contractions. So based on this alone, you should be able to determine what the internal torque is and the external torque. But I'm going to talk it through with you, and then I'm going to let you do the calculation. Because this force, or this vector, is coming from a muscle insertion site, we know that this is the internal force. I will always provide you with that, though. I wouldn't expect you to pick that out on your own, but I do kind of expect you to. But if you're ever on an examination period, I would give that to you. This, then, is your internal moment arm. So this right here, and this is something new that we talked about in class, this is if you were to look at the whole mass distribution of your forearm, we know that gravity acts through the center of gravity. So nothing is being held, there's no weight, there's nobody pushing down. So this is just where is the center of gravity in this lever system, and it's always where the mass is centered around. So let's just say that that's your center of gravity. Okay, G right there, center of gravity. And that's exerting a force downwards of 6. That gravity, weights, somebody pushing, that is an external force. So if that's your external force, then this is your external moment arm. Okay, so I want you to pause the video after this, and I want you to determine what the internal torque is and what the external torque is. So let's do the math. So we know internal torque equals force, or internal force. I should erase that. Sorry, I'll get a thing here and erase that. It is your internal force times your internal moment arm. So internal force is 4 times your internal moment arm, which is 2, so it equals 8. Your external torque is your external force times your external moment arm. And let's look here. Your external force is 6. Your external moment arm is 4. So get out the calculators, and that's 24. Okay, let's pause there, not the video, I'm not saying, but let's pause there from a learning perspective. And let's go over and let's do the exact same thing on this system. Now what we've done is we have just taken and we're looking at a different muscle with a bit of an extended insertion site. So it's a little bit further down the lever, and I'm going to talk to you about what that means. So because this is where brachioradialis inserts on the radial statellite process, we know that that's the point of pull on this lever system. So we're going to call that our internal force, and this is our internal moment arm. This is the center of gravity, again, exerting. So this is going to be our external force, and this is going to be our external moment arm. There we go. So based on this, you should be able to determine what is the internal torque and what is the external torque. So pause it for a second, do the calculations, and let's see if you get it right. So we're back, and the internal torque is your internal force times your internal moment arm, which is 4 times 5, which equals, I'm going to try and squeeze this in, 20. Your external torque is your external force times your external moment arm, which is 3 times 3, which equals 9. So I want you to look at both of these, and I want you to identify all we did. If you notice, and the vectors aren't the same size, they should be in a perfect example, the force of brachioradialis and the force of biceps is exactly the same. So they're working the same. It's just what we've done here is we have extended their position on the lever system. So by extending the moment arm, you increase torque. So look at a force of 4, your internal torque is 8 when it's only 2 units away from the axis. A force of 4 with your brachioradialis when it is 5 units away increases tremendously to 20. So that's an application, and I just want to take a quick aside. When we're working with individuals, imagine if we start working by applying resistance out here and we start going down, you start to increase the force needed as you decrease the moment arm. And I hope that's something you may have to pause and think about that, but that's the application when we head into functionally using it in physiotherapy and occupational therapy. Okay, so let's go back and let's do and draw the directions that these units are moving. So here we know that our external torque is greater than our internal torque. So this force pushing down is, and the torque that it produces is greater than this going up. So the direction of movement is down. Let's go over here, and we see that our internal torque, the torque or the force that's produced by your brachioradialis is greater than the torque that's produced by gravity. So the direction of movement of the unit or the forearm is going up. Okay, one last little application before we head into the next area of figuring things out is I want to look at muscle contractions. And we talked about isokinetic, but we're not going to deal with those. Those are contractions that are controlled by an external mechanism, and they control the velocity and the force of movement. You need a machine to do that. So for our purposes, we have 2 types of contractions. We have an isotonic, and that means that movement's happening. So your lever system is moving. We have an isometric. That means there's no movement happening. So although there are forces that are produced, there's no movement happening. So we're going to look at that in just a second. Your isotonic I want to focus on first, and we have 2 subcategories, concentric and eccentric. Now, if you don't totally understand what those mean, you need to go back to the textbook and you need to do readings on that. Just look back on the glossary and you'll find out where they're located and their definitions. But concentric by definition means, if you look down here, concentric, I'm just going to shorten it, it means that a muscle is contracting, oops, that's an O, N-T-R-A-C, and shortening. We talked about the sarcomeres and the fact that they shorten. So the muscle is actually contracting and shortening. So if I were to put my hand on my bicep, it's contracting and shortening. That's a concentric isotonic contraction. Eccentric, And this is where people get really confused. An eccentric contraction is not a stretch because by definition a stretch means that there is no contraction. So when an eccentric contraction is happening, it means the muscle is contracting, but it's lengthening while it's contracting. So although it's contracting and I can feel it as I go down, it's lengthening. So the muscle is contracting and lengthening. It is not a stretch. That's a passive movement. So let's apply this back to these systems. So here, we already identified the biceps is contracting, but this lever is going down. That means what gravity is exerting, or the external torque that's happening, is greater than the internal. So it's going down. So if I were to draw it, eventually the lever system would be down like this. So although the muscle is contracting, it is lengthening while it's contracting. So a contraction that lengthens while it's contracting is called an eccentric contraction. This is an example of an eccentric contraction. On the other side, this lever system right here is going up. And so this brachioradialis, in a little bit, the system is going to be up here. And so brachioradialis will have shortened. So it's contracting while shortening. And that is a concentric contraction. This is an eccentric contraction. So by definition, eccentric contractions are where the external torque is greater than the internal torque. Concentric contractions are where the internal torque is greater than the external torque. Okay, so one last thing just before we leave. I'd like to do an application to levers. And I'd like you to try and identify what class lever this is. And so if you remember back, there were three components to a lever. There was an axis, there was a force, and there was a resistance. And how those were organized on a rigid system determined the class or the type of lever. So if you remember, type 1 had axis in the middle, resistance and force on either side. It didn't matter which one. Resistance here, force there, resistance there. That was the type 1. Type 2 had axis, resistance, and then force. So I'm going to do, so we remember this, axis, resistance, and then force. And that was a type 2. And then a type 3 switched it and had axis, force, and resistance. So let's look here and let's see. We know that the system is going down. So now we take a step back and we're going to say, what is the force causing that movement? Is the force causing that movement your biceps or gravity? And so if the system is going down, we know that the force is causing the movement is gravity. So I'm going to put this right above. We know the axis is here. And we look here and we say, what is resisting this? Well, if my biceps was not contracting eccentrically to control it as my arm was going down, my arm would just fall down and it would injure my elbow. So we know that it's a lengthening contraction, but your biceps is resisting your arm going down because we know it's exerting a force. So this is a resistance to the force going down. And so if you look at that ARF, what class lever is this? It's a second class lever. Let's go over here and let's look at here. And I'd like you to try and figure this out by yourself based on what's happening. So pause the video and try and figure it out, and then you can start it again. So we need to label this, and we know that the force causing the movement here is your brachioradialis. So let's put it, it's kind of crowded here. Let's put it up here. The forearm is going up, and so we know that brachioradialis is causing that. What is resisting that or adding resistance to that coming up? We know that it's gravity. It's pushing down, so it's resisting the coming up. And we've already labeled our axis here. So again, what class lever is that? It's a class 2. Now let's say, just for application purposes, let's say it gets a little crazy here with all the different things, but let's say I change this to a 10. We would come here, and instead of being 3 times 3, we would now have 3 times 10, which equals 30. Well, now your external torque is greater than your internal torque, and so things are going to change in that the force that gravity's exuding on this lever system is greater than the force that brachioradialis is putting on the system, and your arm is going to go down. So in that case, things change around, and now I want you to tell me what kind of contraction is it that brachioradialis is doing. If it's going down, we know that gravity is causing the force down, and that your brachioradialis is resisting that, and that's called an eccentric, because it's contracting, we know there's a force, but it's lengthening. So instead of going up here, it's going to be down here. Let's label for levers as our last application. We already have the axis labeled. Now, what is the force causing the movement? Well, that's gravity. It's pushing down. What's resisting it? Your brachioradialis is slowing it down and controlling it against gravity. What class lever is that? AFR. That's a third class lever.